Good evening, everyone. So we are again live for the next session of Thermody. Till now, we have completed three sessions on Thermody, in which various important terms have been discussed already. Two processes were also discussed in the previous lecture. Uh, I think you all are aware of that. In the previous session, if you can remember, we have done a lot of questions. Uh, the level was up to JE mains, or the conceptual based questions we have picked. So in today's session, first of all, uh, bring a notebook with you because we are going to uh, do lot of things today. The content is pretty much more as compared to the previous lecture, because in the previous lecture there were a lot of numericals. In this session, there will be this is going to be a theoretical session. So you need to write down things that would be better for you. So first of all, let's see what's we are going to study in today's lecture. Okay. First of all, there will be a recall test, very small recall test. Then there will be some definition things, some important concept like degree of freedom, uh, specific heat, then specific heat for a gas at constant volume, constant pressure. Then we will study about adiabatic process and then their slopes. After that, there will be a simple concept test for you, which is going to be a previous year question of mains. And after that, we will summarize the things. And that's it for today's session. Okay. So let's start our journey. Take your pen and paper out, and try to solve the first recall test. Okay. So what is it? The question says, in which process temperature is decreasing? This is a very simple question, actually. If you can see, the question is very simple. In which process temperature is decreasing? That's what you need to define. And for that, you have 40 seconds. You have 40 seconds to answer the question. Okay, so I'm waiting for 40 seconds. Roughly 40 seconds I am waiting. To solve this question, actually what you need, the basic things, the basic indicator diagram knowledge that you should have. Okay, so we will uh, try to solve question by options. Actually, in this case, you need to check the options. There is no other choice. Or you can see that in first option, in option number A, the PV graph indicates that this is the isothermal curve. This is a isothermal curve. So if this is isothermal curve, then you can see that T is constant. It might be an adiabatic curve, but I will not go into that situation because you have not studied the adiabatic condition till now. So for this case, up to now, this is going to be our isothermal curve. But you will see in the later section that adiabatic curve will also look like that, look the same. So we will do that. We will discuss that later. Okay. So till now, it's isothermal curve, and isothermal means temperature is constant. If you go with option B, if you check the option number B, in this case, this is a isobaric process. This is what? Because pressure is constant. So this is isobaric process. And in isobaric process, what you have seen that V is proportional to T, that we have studied in the previous section. V is proportional to T. So you can see that volume is increasing. For the process, volume is increasing. If volume is increasing, then temperature is also increasing. So in this situation, temperature is increasing and they are asking about the decreasing temperature. So option B is also wrong. In option C, if I say this is P versus T graph, and from the graph, it is clear that this is P proportional to T. This is P proportional to T. If P is proportional to T, you can see that in the process, according to the arrow, if you see the arrow, this is initial state, this is final state, and pressure is decreasing. If pressure is decreasing, then okay, there is no problem with that. Temperature is also decreasing, and you can see that temperature from A to B is decreasing like this. This is initial temperature, and this is final temperature. So you can see by that as well. And if P is proportional to T, then which process is this? This is isochoric process. This is isochoric process. And which process is process number 4? Option D is what? Temperature is constant. So this is again isothermal process. This is again isothermal process. So in which option, in which process temperature is decreasing? In option C, temperature is decreasing. Option C is the correct answer. Now on the next slide, there is a question, a recall test. Try to solve it out. The question is, you can take 1 minute to solve it. You can take 1 minute to solve it out. And you need to answer the question. The type of questions that I am picking here are all mains level question and are previously asked in mains. So don't take them lightly actually, or don't think about that we are not good enough to solve the questions. Actually, you can do these questions, and these are basic fundamental questions. And most of the times questions were asked on these concepts. Try to solve it. Most of the times students gets confused how to start, what should be the approach, and how to start the question. So that's the main question that comes to the student's mind. So it will be easily resolved by practicing. And I think everyone should at least try to read the question. Okay. So question says, okay, so first of all, we will remember they are talking about 2 moles. So N is 2. Monoatomic ideal gas are taken through the process P into T is equals to constant. So they are not defining the name of the process. They are saying that P into T is constant according to the question. And it again says its temperature is increased from T naught to 2T naught. Okay. The work done in the process will be. Okay. So we need to calculate the work done in the process. Clear? So whenever work done is asked, for any process, you can start with, whenever work done is asked, you can start with work done is equals to integration PdV. Clear? That's what the approach is. Now we need to put the value of P, but given is P into T is constant. So let's try to write down some values here. Okay, okay, okay. What is given? P into T is a constant. So can you see that constant, let's suppose is K. Is it clear? Again, if P into T is a constant, let's suppose this is equation number one. Can you write it as P1 T1 is equals to P2 T2 is a constant K? These are the same things written. And we again know that PV is equals to nRT. Is it clear? These three things we know, and what we need to do, we need to put the value of P. We need to put the value of P in terms of V, because we are going to integrate in terms of V. So try to manage things like that. Okay. So from here, can you see that if I change, can you see that T is equals to PV over NR? Is it clear? T is equals to PV over NR from this equation. And if I put this value of T in 1, so it will be P into T is what? PV over NR is equals to constant K. So P is what? nRK over V under root. Is it clear? So what was our aim? Our aim was to calculate P, to find P in terms of V. So we have got P in terms of V. Now we will place this value of P in equation in this work done. So now placing the value, work done is equals to integration. P is what? Root of nRK divided by V into dV. Now N is number of moles, R is gas constant, K is a constant. So all these terms are constant. We can take it out of the integration. So W is equals to integration के बाहर nRK. What is left? Integration 1 over root V dV. From where to where you will integrate? From V1 to V2 you will integrate it. I think up to this point everything is clear. Moving further. Now you just need to integrate the question. What will be the work done? W is equals to, or work done is equals to root of nRK. 1 over root V integration is what? Will be 2 root V. I think integration part is up to you, na? You can integrate it. 1 over root V, you can integrate it root V to root V. And limit is from V1 to V2. I think it is clear. Right. Now again, W is equals to 2 times root of nRK. Limit, if you put the limits, it will be root of V2 minus root of V1. I think till now everything is clear. We are doing just simplest things. Now again, I am just putting further few values. I am multiplying this root nRK inside the bracket. So W is equals to 2 times root of nRK and V2 minus root of nRK V1. I think clear. Okay. So What's given in the options is RT naught, RT naught, RT naught things. So we need to eliminate this volume because volume was not given in the question. We are dealing with volume V1 and V2, but volume was not given. So we need to eliminate those things from the equation. So what it would be, W is equals to, a work done is equals to 2 times. Now, what is the value of K? You can say K is what? Either P1 T1 or P2 T2. When there is a term V2, I will place the value of K P2 T2. So I am placing the values root of NR V2 and K is what? P2 T2 minus root of NR V1 is already there. K is what? P1 T1 bracket closed. Okay. Now again you can see that this P2 V2 is what? You will say NRT2. P2 V2 is what? NRT2. And P1 V1 is what? NRT1. So can you see that it will become under root NRT2 square? It will become NRT1 square and under root will be cancelled out. So what will be the work done? Work done will be 2 times NRT2 minus NRT1. Now you can see that work done is equals to 2 times NR T2 minus T1. Now you know the values, you can place the values. What are the values given? If you place the value, W is equals to 2, number of moles are 2, R, and T2 minus is what? T2 minus T1, 2 T naught minus T naught, that is T naught. So the answer is W is equals to 4R T naught. Someone of you might feel like that this is a longer question, this is a tough question is on the tougher side, but this is a basic question actually. So correct option is B. Correct option is B. You could have done that question. You could have done that question. In any step, if you feel anything, the basic agenda of the question is what? The basic agenda of the question is whenever you need to calculate work done, you will start with PdV. If no other function, no heat is given, no first law of thermodynamics can be applied, then you will start with PdV. Then if pressure is constant, take the P outside of integration. If pressure is not constant, then place the value of P in such a way that you can integrate it because you are going to integrate in terms of volume. So make some modifications in such a way that you can integrate that. After that, what's given in the question, you can put that. That's what should be the approach. Try to solve lot of such questions, and you will be familiar with this. That's why I'm taking a lot of questions from this condition. Okay. So now moving further. Okay. Degree of freedom. This is a topic that I'm taking here because this is a topic of KTG. We will study in KTG in more details. So till now, I'm just picking the topic because we will need some help from these degree of freedom. A lot of questions come from this topic in thermody. So what is it? Degree of freedom is what? Name suggests something they are talking about freedom. So I have told you in the first or second session, first or second lecture of this thermody that a gas may have energy due to its translational energy, its rotational energy, its vibrational energy, or the combination of these. So degree of freedom is what? The number of ways a system or a molecule can acquire energy is degree of freedom. The total number of independent ways in which a system can possess energy is called degree of freedom. I think it is clear. The definition is clear. And what are these ways? I have told you in the previous sessions that translational energy, it can be translational, it can be rotational, it can be vibrational, or any combination of these. So we are not going in deep detail of these definitions because it is a part of KTG. So we will study it there. So right now, what you need to remember, this is the basic idea of degree of freedom. What you need to remember, there may be three types of gases you will face. You will see the names of three type of gases. One is monoatomic, like helium, neon, argon. One is diatomic, like oxygen, nitrogen, O2, N2, H2. These are the uh, diatomic. And then there comes polyatomic, like ammonia. This is a polyatomic. So at room temperature, their degree of freedoms are known. And you need to remember these degrees of freedom. At room temperature, I am talking about. So for monoatomic gas, degrees of freedom are three. For monoatomic gas, degrees of freedom are three. You need to remember this. Sorry, actually, I am having some cold now. That's why. For diatomic gas, degrees of freedom are five. And for polyatomic gas, degrees of freedom are six. I'm talking about these values at room temperature, and most of the times, room temperature is given. They deal with the room temperature things. So, what you should remember these values first of all. 356, 356, monatomic 3, diatomic 5, and polyatomic 6. Clear? Polyatomic means there might be triatomic, tetratomic, whatever may be the situation, but it will be 6. Clear this point? Remember. Okay. Now moving further. Internal energy in terms of F. F is what? Degree of freedom. So internal energy is a function of temperature that we have seen in the previous sessions. Now internal energy can also be defined in terms of degrees of freedom. What is that formula? Again, you need to remember this term. We are not going in deep detail how this formula is achieved, but you need to remember this term. Delta U is equals to, sorry for that again. NR delta T, again, N is number of moles, R is gas constant, delta T is the temperature difference. F by 2 is what? F is degrees of freedom. You need to again remember this term. We will drive it in the KTG section. Right now, just remember it. Delta U is what? Internal energy, or you can say change in internal energy. We will relate these terms in the later section. So right now, what I have told you, degrees of freedom for monatomic gas 3, diatomic gas 5, polyatomic gas are 6. At what? At room temperature. Internal energy in terms of degrees of freedom is F by 2 NR delta T. Till now, I have asked you to remember these two formulas. Write it down on your paper. Write it down. Okay. Now there comes a term specific heat. Again, try to remember this term. This is a simple definition. You can easily find it now. Have a look at that. Let's suppose you have a body which has a mass m. You have a body which has a mass m, and you are heating it. You are heating it by giving some energy Q. Let's suppose you are giving it some energy Q. And by this energy, its temperature is increasing from T1 to T2. Or you will say temperature rise is what? Delta T. There is a body of mass m, you are heating it by giving some energy q, and its temperature is rising from T1 to T2. Or you can say total rise in the temperature is delta T. Then it is found that what is found that this external heat given or q is directly proportional to m delta T. That heat given to the system is directly proportional to the m delta T, where m is the mass, delta T is the change in temperature. So if I remove this constant of proportionality, there is a constant q is equals to T is a constant m delta T. And this constant C is called specific heat. This constant C is called specific heat. So what is important from this simple term, that you need to remember this formula: Q is equals to Cm delta T. C is specific heat, M is mass, delta T is the temperature rise, or it might be in some cases temperature fall when Q is rejected by the system. So there is no issue with that. Q is equals to Cm delta T. C is what? Specific heat. From this term, I am going to define C. I am going to define C. I am making a definition for C. C is what? Specific heat. For that, I'm assuming some things like if M is equals to 1 kg. 1 kg means unit mass. If mass is unit and delta T is also unit. Unit, it might be 1 degree Celsius or 1 Kelvin. Both will be same because temperature difference is same in both the cases. So delta T is, I am supposing, 1 Kelvin. So if M is 1, delta T is 1, then you can see then T will be equals to Q. T will be equals to Q. So from this assumption, a definition can be made for a specific heat. And what would be that definition? Listen to me. A specific heat, C is what? The heat required. C is what? Q. So C is what? The heat required to raise the temperature of a unit mass. M is what? Unit mass by 1 Kelvin. By 1 Kelvin is called specific heat. So you can see the definition here. The heat required to raise the temperature of a body of unit mass by 1 Kelvin is called specific heat. So you can repeat the definition with me, along with me. Heat required. What is specific heat? The heat required to raise the temperature of a body of what? Unit mass. By what? 1 Kelvin. This is simply called specific heat. I think till now, a definition of a specific heat is clear. Clear. Now, remember one thing. Specific heat is what? The heat required for what? For raising the temperature by 1 degree Kelvin or 1 Kelvin of what? Of unit mass. Clear? In the same way, molar specific heat is also defined. Molar specific heat is the heat in which mass is replaced by molar mass. So there is nothing special with that. Okay. So now we are moving again further. Specific heat for a gas. In the previous definition, I am dealing with the body. This is a body, any body. Now I am dealing with the gas. There is a problem with the gas. What's the problem with the gas? Like solid, if you heat the solid, the change in its volume is very low or negligible. You can neglect the change in the volume. But in case of gases, when you heat the gas, when you give some external heat to the gas, then its volume and pressure both may change. Listen to me very carefully. When you give heat to a body, then its pressure and volume both may change significantly. And if both are changing along with the temperature, then the rise of temperature depends on the factors by which volume and pressure are changing. You are not getting what I'm saying. For example, you have a gas in a container like this, and you are giving some heat to it. The intention of giving heat was to raise the temperature, but unfortunately, the volume and pressure also changes. So these are two unnecessary things. So the heat required to raise the temperature by 1 Kelvin, can you see, may also depends on the conditions of pressure and volume. That's what I'm trying to say. That means heat given or heat required to raise the temperature by 1 Kelvin will not going to be same, is not going to be same. Why? Because it may depends or it depends on the conditions of pressure and volume as well. So what I'm saying, the thing that I'm saying is mentioned here. When heat is supplied to a gas, then its volume and pressure may change along with its temperature. So if pressure and volume are also changing, then what will happen? Amount of heat required to raise the temperature by 1 Kelvin is not fixed. Sometimes you will need more energy, sometimes you will need lesser amount of energy. It depends completely on the conditions of pressure and volume. That means, what does it mean? The heat required to raise the temperature by 1 Kelvin is what? Is what? Is specific heat. Is what? Is specific heat. So specific heat of a gas is not a constant number. This means that specific heat of a gas depends on the condition of pressure and volume which is heated. And this means C is not constant. C is not constant. For what? For gases. Now, till now, what we have seen that for most of the solids and liquids, specific heat capacity is constant. Specific heat is constant. But for gases, it is not constant. That's what we have discussed. But if it is not constant, then what values it can take? There are a lot of conditions, lot of situations, but the crux is that the specific heat for gases may be positive, may be negative. That's the important thing that I'm saying. A specific heat of a gas may be positive and may be negative. Right? This is an optional question. Once came in the examination. So the option you need to remember that a specific heat of a gas can be positive, can also be negative, and it may take any value from 0 to infinity. It can take any value from 0 to infinity. I think the concept behind specific heat of gas is clear. Why it is not constant, it is clear because it depends on the parameters on which pressure and volume varies. I think this slide is clear. Moving further. Now, there might be various situations, various conditions on which P and V value changes. The two very famous situations I am dealing with, or we deal with, what happens? Okay. One is the condition in which volume remains constant, only pressure is allowed to change. Listen to me. We are dealing with the specific heat of a gas. there will be a lot of conditions of pressure and volume, like pressure is allowed to change slowly, volume is allowed to change slowly, but out of which what we are dealing with two conditions. What are the two conditions? First condition is that in which volume remains constant and pressure is allowed to change. Clear? So specific heat at constant volume is what? The heat required to raise the temperature of 1 mole of a gas by 1 Kelvin at constant. The definition is same. What's We are dealing with molar specific heat actually. In terms of gases, we deal with number of moles most of the times. That's why I am writing moles. I'm not writing the kg. I think clear. The heat required to raise the temperature by 1 Kelvin of 1 mole of the gas by keeping volume constant. So volume is constant. You need to remember that. And it is denoted by CV. It is denoted by CV. Now listen to me very carefully. You can see that Q is equals to what we have seen, that MC delta T. We have seen that now. What we have seen, Q is equals to MC delta T in terms of solids. Now, M is what we are taking number of moles. It can be written as N C delta T. But C is what? At constant volume, so it is denoted by CV. So this is a relation, Q is equals to NCV delta T. You can remember or you can make it on time. No problem with that. Now, again, listen to me. There is going to be one more simple term. If I say, if they are dealing with constant volume means, can you see that isochoric process? What is the meaning of constant volume? Is it isochoric process? If they are talking about isochoric process, then again I can see that from first law of thermodynamics, Q is equals to delta U plus W. And for isochoric process, work done is what? Zero. So delta U is what? Q. So delta U will be Q, and Q is what? NCV delta T. This is again an important factor, that change in internal energy of a gas is defined as NCV delta T. Internal energy NCV delta T. Clear? Till now, everything is clear. Moving further. Make note of this formula. Moving further. So what we have seen is specific heat of a gas is not a constant. It may be positive, it may be negative, it may take any value from 0 to infinity. One thing. Why it is not constant? Because it depends on the conditions of pressure and volume as well. Specific heat of a gas. Now, the two important conditions are specific heat at constant volume. The first condition is when we are dealing with constant volume and gas is being heated. So in that situation, what we have found, that delta U is equals to NCV delta T. You can relate this equation. You can reform this equation. Now, another heading is that CV in terms of F. What I am saying, I have put a disclaimer before the class that there will be a lot of formulas, lot of theory discussion. So be aware of that and be prepared for that, I will say, because there are going to be a lot of formulas and there will be chaos in your mind about these formulas. So be prepared. Again, CV in terms of F. So they are asking me to find the CV. CV is specific heat at constant volume in terms of F is what? Focal length. F is what? What is F? Can you answer? F is what? Degree of freedom. F is what? Degree of freedom. So what we have seen till now, we know that previously we have seen that delta U is equals to F by 2 N R delta T. Do you remember that we have written this equation? Delta U is what? F by 2 N R delta T. And we also know that we also derived right away delta U is equals to NCV delta T. I think you know these terms, huh? We have defined them earlier right away, right before one or two slides. So if you compare these two equations, comparing 1 and 2, what you will get, NCV NCV delta T is equals to F by 2 NR delta T. You can cancel few things, delta T, N and N. So what's remaining? CV is equals to FR by 2. CV is equals to FR by 2. What is R? Gas constant. What is F? Degree of freedom. 2 is a constant. So one more thing that you can form here, you can remember. You can actually remember here. You can actually remember the value of CV because you know the degree of freedoms. R is a constant. So you can see that CV is a constant term. CV is a constant term. From this equation, you can see that CV is a constant term. For monatomic gas, for polyatomic gas, for diatomic gas, F is known. So you can put these values, but these values are at room temperature, are at room temperature. So I'm not going to put these values because it will waste a lot of time. You can place F is equals to 3. I am putting some values. Okay, at room temperature for monoatomic gas. For monoatomic gas, F is what? You can see for monatomic gas, F is what? 3. If F is 3, then you can see that CV is equals to 3 by 2R. Similarly, you can place the values for diatomic and for polyatomic gases. You can place the values by yourself. Should I move further? So you need to remember CV is equals to FR by 2. Remember, CV is equals to FR by 2. I am moving further. Specific heat at constant pressure. It is denoted by CP. That this is the same thing. What's changing here? We are keeping the pressure constant and volume is allowed to change. The heat required to raise the temperature of 1 mole of a gas by 1 Kelvin at constant pressure. Nothing changes. The same definition, the same thing, but only the pressure remains constant in this time. Okay. Now there is a node. Now we have two types of specific heat capacity, specific heats. One is at constant pressure and one is at constant volume. One is denoted as CP, other is denoted as CV. So the thing is that Cp is always greater than Cv. Cp is always greater than Cv. There is a logic behind that as well. If you ask me, I will define it to you. Right now, I am moving further. I am asking you to remember this thing that Cp is greater than Cv. And the difference between these two, and the difference between these two is nothing but, and make sure that difference between these two, Cp minus Cv is equals to the R. This is again a golden equation. And this equation is called Mayer's formula. Mayer's equation. Cp minus Cv is equals to R. You can check out the derivation from your NCRT book, but the relation is important for us. That is Cp minus Cv is equals to R. Cp minus Cv is equals to R. And what is the result? Why this result is important? Because Cp is always greater than Cv. I think till now everything is clear. I am moving further. Again, the heading says Cp in terms of F. Cp in terms of F. So what we know, we again know that what we know that Cp minus Cv is equals to R. Cp is equals to Cv plus R, you can say. And Cv is what? I have told you Fr by 2 plus R. So Cp is going to be R is common, F by 2 plus 1. Okay, so there are a lot of formulas till now. There are a lot of formulas till now. Now it's your turn to answer few questions. It's your turn to answer few questions. Now tell me the value of Cp. Tell me the value of Cp for monoatomic gas. For monoatomic gas. Tell me the value of Cp for diatomic gas. Tell me the value of Cp for finally monoatomic gas. Tell me the value of Cp. It's your time to answer. Tell me the values of Cp for monatomic, diatomic, and mono. Okay, mono. It's not mono. It's uh, polyatomic. Okay. Can you answer? For monatomic gas, F is what? 3. So it will be 3 by 2 plus 1, 5 by 2 R. It will be 5 by 2 R. Okay. For diatomic gas, F is what? 5. If F is 5, you can place the value 5 by 2 plus 1, that is 7 by 2. 7 by 2 R. And for polyatomic gas, this value is what? F is what? 6. If you place the value of 6, that will be 3 plus 1, 4R. You need to remember these values. You need to remember these values. I think it is clear now. Now we are moving further towards adiabatic process. This is again a important thing, most important topic, adiabatic process. So what is adiabatic process? The process in which heat cannot be exchanged between medium and surrounding. For example, if this is a container, this is a thermodynamic system, then during the process, heat transfer is not allowed. The process in which no heat transfer takes place between system and surroundings. The process is known as adiabatic process. I think step is clear. You can remember this thing by adiabatic. Adiabatic walls we have studied, in which I told you that adiabatic walls are the insulating walls. So adiabatic process, you can remember it from there, that no heat transfer can take place. I think clear. Now, one more thing that you need to remember, I am not going with the derivation part. The thing is that whenever there is an adiabatic process, it follows a certain rule, and that certain rule is called Poisson's law. Poison is everywhere. Poison is everywhere. Some persons are poisonous, some laws are poisons. So poison is, you can see everywhere. Like you have studied Poisson's ratio. I think you know the term Poisson's ratio when we are studying with properties of solid. So the Poisson's law, and it says for adiabatic process, for adiabatic process, P into V raised to the power gamma is equals to constant. This is what Poisson's law. This is going to be a very typical situation for some of you when you are dealing with powers gamma. So for adiabatic process, what's the condition? P into V raised to the power gamma is a constant. And what is this gamma? What is this gamma? This gamma is called adiabatic constant. This gamma is what? Adiabatic constant. And what is its value? What is its value? It is a constant, and it has some value. And the value of this adiabatic constant is Cp over Cv. The ratio of Cp over Cv is called gamma. I think clear. You can make it in a box. Uh, 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 uh. Now you know the value of Cv, you know the value of Cv. Can you find the value of gamma? Can you find the value of gamma? Yes, you can. Cp is what? If you see, Cp is what? R f by 2 plus 1. And Cv is what? Fr by 2. You can place these values here. Gamma is equals to Cp is what? R f by 2 plus 1. This is what Cp divided by Fr by 2. Now you can cancel out few things. R and R get cancelled. Gamma will be You can take the LCM, F plus 2 divided by F. You can easily see that. So gamma is going to be 1 plus 2 by F. Now again, you know the value of F, so you can calculate the value of gamma. And you need to remember the value of gamma. Question In the question, the value of gamma is not given. So you need to find it out. You need to remember this value. And how you can remember this value? So I am making gamma for you. For monoatomic, for diatomic, and for polyatomic. You can find the values of gamma. For monoatomic, again F is 3. For diatomic, F is 5. For polyatomic, F is 6. Clear? If you know the values of F, you can write the values of gamma as well. Gamma is equals to 1 plus 2 by F. That is 1 plus 2 by 3. 3 to 5. 5 by 3. 5 by 3. In case of diatomic, that is 5 plus 2, 7 by 5. And in case of polyatomic, 4 by 3. Check the calculation. Check the calculation whether I am right or wrong. If I calculated these things right, clear till now? I think everything is clear till now. Moving further. What are the conditions for adiabatic process? Okay, listen to me. What is adiabatic process? The process says, for example, this is a thermodynamic system with a piston. And this is some gas, ideal gas. So what I'm saying, that heat cannot be exchanged. Heat cannot be exchanged means the walls should be adiabatic. Can you see that? That walls should be adiabatic because heat transfer is zero. Q is what? Zero. That means walls should be adiabatic. So first condition is there, walls should be adiabatic. Next condition is that if you come to the real life, there is nothing as perfectly insulating. There is nothing as perfectly insulating. However, insulating thing is, but it can transfer a small amount of heat. It's quite possible that heat may be transferred. So, how generally you can say practically adiabatic process is not possible because heat transfer is possible with any surface, with any kind of walls. You can assume that, for example, I have this bottle. They claim that water will remain cold up to 24 hours, I think. So after 24 hours, what will happen? That it can maintain up to a certain limit. Now, after that, heat is transferring. If it was so, then heat can never be transferred, then body will remain colder, body will remain hotter for the entire life, but actually heat transfers. So in that case, the suggestion is that what if we just don't give time for the transfer of heat? Like we are not giving time for the transfer of heat. That means the process should be very quick. The process should be very quick. If the process is very quick, that means you are not giving time for the transfer of heat. You are not giving time for the heat transfer. So that's how the adiabatic processes are achieved. Like you can say a simple example, you have a balloon uh, uh, filled with air kind of thing. You blown the balloon and it's filled with the air, and you just opens its mouth. Then the gas comes out of it very quickly. The process is very quick. You can see that the process is very quick, and such kind of processes are can be named as adiabatic process. Like uh, the wheel of your car, which has in some air in it, and you just uh, what आप उस टायर की हवा निकाल देते हो. So जैसे आप उसको पिन लगाते हो, then air comes out of it very rapidly. That process is also an adiabatic process because that process is happening very quickly. Adiabatic process is what? The process in which happens very quickly. That may be regarded as adiabatic process. I think till now everything is clear. So I think time is up. So we will wrap up the things here. What we have learned today, we have learned a lot of things, like we have learned about degrees of freedom. So what are the values of degrees of freedom? I think you can remember those values. For monatomic, it is 3. For polyatomic, it is 6. For diatomic, it is 5. After that, what we have studied about the specific heat, the heat required to raise the temperature by 1 Kelvin of a unit mass. Then for gases, what about gases? In case of gases, the specific heat is not constant. Why it is not constant? Because it depends on the conditions of pressure and volume, because it may also change significantly. Out of these values, you can say it may be positive, it may be negative. Look at me. Specific heat of a gas may be positive, may be negative. It depends on the conditions of pressure and volume. Another thing is the value of a specific heat of a gas can take any value from 0 to infinity. Clear? The two famous conditions of specific heat of the gas are at constant volume and at constant pressure. So we have dealt with the constant volume and constant pressure. After that, we have studied adiabatic process. In the adiabatic process, what are the necessary conditions for adiabatic process that are mentioned on your screen? What is the law that it follows? It follows Poisson's law, that is PV raised to the power gamma is equals to constant. Gamma is what? Adiabatic constant. What is the value of gamma? Gamma is Cp by Cv. Clear? And the numerical value, you can say 1 plus 2 by F. I think till now everything is clear. So we will start our session from tomorrow. Till then, enjoy your day, enjoy your Sunday, and I think bye bye.